sheet is figuring out the position of the bus and girl at any time step. We can also show it in position here. So if we don't have to go by 0.1 seconds, I could jump this up to 1 second and then continue my graph. And now you can see that even though I don't have any information in between, I am starting at the right points. So I could go to 2 seconds, and then 3 seconds. And you can see how we still know where it is at that any point in time we're calculating, but we don't really see what's happening in between. But since the time step doesn't matter, and these equations, these patterns hold, we can expand these out to something a little more interesting. What we did here, we used these 3 equations circled in yellow, and we've used those to find the position of the girl in the bus at any point in time, depending on our time step. So what we're going to do here is we're going to expand those out a little bit. And let's look at our first one, that the average velocity was equal to the change in position over the change in time. Now remember that delta just is the same thing as change. And we always find the change by taking the final minus the initial value. So if you went to the casino with $80 and you came home with $40, that means that your change would be negative 40. So, or you went down by $40. So the idea of calculating change, that works for anything that we're doing, position, time, or casino spending. So we'll keep that in mind here. And so we're going to do a little bit of algebra now, algebra with letters, everyone's favorite kind. I'm going to solve this equation for delta x, and I do that by multiplying both sides by delta t. So I get V average delta t is equal to delta x. I'm going to rearrange that here. I'll put delta x on the left side, V average delta t. And now I'm going to put in what delta is equal to. Delta x is equal to the final position minus the initial position, V average. And now delta t actually is equal to the final time minus the initial time. So let's solve this for xf. X final is going to be equal to the initial position plus the average velocity multiplied by this delta t. Now, if our initial time, usually we start that at 0. And so now I just have left Vt final. Okay, so now this equation is interesting because if I just say, let's think about this for any point in time. So T final will just be whatever time we're looking at. Now I have a function. The position as a function of time is going to be equal to its initial position plus the average velocity times time. Now we can graph this one. This is a very graphable one. So if let's see if we graph this for where's our Desmos? Guess we need a new Desmos. So if we think about this one here, if we do this for the girl, let's type this in. Lately I've been liking to add notes. So we have a note. We have x is equal to V average times time. And if we put it in here, we get x equals V average. So for the girl, it's just 5.5. And then we're going to multiply by time. All right, and Desmos can graph that for us right away. Let's see. So there it is, and this shows the girl as a function of time. It's a lot easier on the iPad to zoom in and out on here. You can also add subscripts. You do that by doing the underscore key. So now I can have this as the position of the girl. Okay, so this can be a little bit handy here. We could also do a slider for T and kind of expand that out, but we won't go. So that'll be the girl's position. We can graph that. We could also think about we could do the bus's velocity pretty easily because that's a very similar equation. If we do the same kind of thing here, but instead of V average is delta x over delta t, if we expand that out to acceleration is equal to change in velocity over the change in time, we can do these same steps, v final minus v initial, t final minus t initial, and we can take that out and show that velocity as a function of time is going to be equal to our initial velocity plus the acceleration times time. So we're moving from delta t's to just any point in time, so we can graph this. So if I put this one on here, the velocity of the bus is going to be equal to the initial velocity of the bus, that's where the I comes from, plus 1.5 t. So we can graph that also on Desmos, put it in here. Now we got the velocity of the bus. Oops, gotta do the underscore. Remember, I'm only typing with one hand here because my broken shoulder. Is going to be equal to the initial velocity of the bus, so it started at 0, plus 1.5 times time. So that green line now is the velocity of the bus. You can scroll it. So we can see that the bus is increasing because there's a constant acceleration. Well, what we really want, though, is the position of the bus, so we can compare it to the position of the girl. And if we look back here, how do we get the position of the bus? Well, it was 2 steps. First, we found the velocity of the bus, and then we used that to find the average velocity, and then we used the average velocity to find the position of the bus. So we basically combined these 3 equations together that are in yellow. And so let's see if we can do that with algebra. So this is going to be our last equation, I promise. So let's see, let's do something powerful. Let's do purple. So we have this whole equation. We want to find the position of the bus. And if I start with the delta, the V average equals delta x over delta t, we showed how that changed into the position as a function of time is equal to the initial position plus V average times time, right? That's what we showed. All right, well, we have another equation here, and that actually tells us what V average is equal to. So V average was actually equal to the final velocity plus the initial velocity divided by 2. All right, well, let's put that in. So if we combine those 2 equations, we get that the position as a function of time is equal to its initial velocity plus, now let's not write V average, let's write V final plus V initial over 2, with parentheses on that. So where V average was, we stuck in that average formula and multiplied by T. All right, well now V initial was given to us, but what about V final? Well, we just showed up above here that V final, there was, is equal to any velocity is equal to initial velocity plus the acceleration times time. So that's using this third equation. So let's plug that in. So we have this equation here that V final is equal to V initial plus the acceleration times time. And you can see how that one right there comes from this one right here, that V final, or any velocity at any point in time, is equal to its initial velocity times the acceleration plus the acceleration times time. And when we plug that in here, let's see what we get. We get x of t is equal to its initial position plus, now we got to do a little algebra, we got vi plus at, that was my v final here, that's what that was. Now plus vi all over 2, and then we have that parenthesis t. Okay, so let's we got some terms that we can combine here. Xi, let's do this inside first here. We got a vi and a vi, so that's going to be 2vi. Then we got the plus at, and that's all over 2, and that's all times t. So let's distribute this t across. So we still have the xi by itself. You can see the xi. And now let's distribute that t. So we get we get 2VIT plus AT times another t. This t comes over, so we get AT squared, and that's all divided by 2. Oh, but I forgot the plus. All right, well, we can simplify these up. We can divide both sides by 2. So we get x of t is equal to xi, the initial position, plus 2 vi delta t divided by 2. The 2's cancel out. So I get vi times t plus, and then I got at squared divided by 2. So that 1/2 is there, at squared. So this is going to be your good friend. We actually called, some years we call this the master equation because we use it so much. But what it does, it allows you to calculate any position at any time if you know where it started, how fast it was going when it started, and what the acceleration was. So this only works when you have constant acceleration, so just a single value for A. But that works for this bus problem. And if we put it in here to Desmos, we can do this all at once. So we got the position of the bus was going to be equal to, start at 10. The initial velocity was 0. I'll put this in here just so we can see it. And then we have plus 1/2. The acceleration was 1.5. And then we have to multiply that by t squared. Oops, not that parentheses. T squared. All right, we put that in. We can't see it because it's actually off the screen here. So if I adjust my view a little bit, so the x-axis, we want to go from 0 to 4, or 0, I'll say 0 to 5. Our y-axis, we're going from 0 to, oh, what does it go? Maybe up to 20 or 25. Okay, and then I can get out of here. So the green line, again, was our velocity. I'm actually going to get rid of that for now. Let's see, I can just delete that out. Still the equation. And now we can see here, here is the girl starts at 0. The bus starts at 10. The girl has a constant velocity, which gives a straight line on a position graph. And the bus has a curved line because it's accelerating. So it's curving upward because it's a positive acceleration. And now we can kind of see visually here that it looks like they're pretty much catching up to each other at some point here. And if we zoomed in even further, we can see that if we click on it, you can see that, oh, look, they're equal here and they're equal here. So that was the first point we found, like, oh, look, at 4 seconds, they're both at 22. So we knew that they had caught up. But actually, the girl caught up at 3.33 seconds. And she was actually ahead of the bus here until the bus caught back up to her at 4 seconds. So that can be a much more powerful tool of using these equations to solve problems, which is what you get to do in the next assignment with it, and the book assignment. So hopefully this helps you.